Hi and welcome to this SUSECON Digital 2022 talk entitled Benefit from an eBPF Kubernetes Network Data Plane with Calico Open Source. This is a technical intermediate level talk. So eBPF is a way to write mini programs that can be attached to various low-level hooks within the Linux kernel. It's suitable for a wide variety of use cases, including networking, security, and tracing. It offers performance advantages whilst maintaining reliability and security. Calico Open Source is the most widely deployed container network interface, or CNI, for Kubernetes, and it offers a data plane implemented with eBPF. We'll review what the benefits of that data plane are and what you need to be aware of to decide whether it's the right fit for your cluster. Hopefully you'll walk away with the knowledge to make your Kubernetes clusters faster and cheaper, and also add a few killer features. So a quick agenda, we'll have a Kubernetes networking overview, then an eBPF technology overview, and then I'll dive into the benefits of applying eBPF to the Kubernetes network data plane so we can understand why Calico offers that choice. But first I should introduce myself. My name's Chris Tomkins. I work for Tigera, the primary contributor to Project Calico. I'm lead developer advocate. I've been working in networking for about 20 years. I became increasingly interested in software-defined networking and infrastructure as code, and that brought me towards Kubernetes and Calico. So let's get into a Kubernetes networking overview. So the Kubernetes project defines something called the Kubernetes network model. This diagram will help us to understand it. The Kubernetes network model defines a set of rules for what network forwarding needs to look like in a compliant Kubernetes cluster. Now, I alluded to this earlier, but the Kubernetes networking is actually implemented by something called a CNI, or Container Network Interface. That's not actually part of Kubernetes. So you can consider it to be that the Kubernetes network model defines what the specification looks like, and then the CNI, or Container Network Interface, goes ahead and implements that network model. Some components of the network model are optional, and I'll point out the key ones as we go forward. So Calico is a CNI choice for a Kubernetes cluster. Now, let's dive into the network model. So the first thing to point out here is that we have pods, and inside each pod we have containers. Now, you can have multiple containers within a pod, but they don't have their own IP address. The Kubernetes network model defines that each pod has its own IP address. So pod A has 10.0.1.2 and pod B in this example has 10.0.1.3. This is a simple flat layer 3 network. That means it's all routed, there's no switching or broadcasts here. And every pod is aware of the IP address of every other pod. That is to say, they can all forward to each other with no restriction within the cluster. There is also no network address translation, or NAT, inside the cluster. So that's shown with the red in the diagram. You can see that a packet traveling from pod A to pod B maintains the source IP address of pod A and the destination IP address of pod B all the way through the network, and the return traffic, the same can be said. Now, having just said that everything can reach everything else, obviously that's not always desirable in a production or testing network. So the Kubernetes network model offers this thing called network policy. And you can see that shown here as a data structure at the top. The reason it's shown as a data structure is that the Kubernetes network model offers a resource type for network policy, but it doesn't mandate that the CNI must implement it. Some CNIs do implement network policy and some do not. That's an important consideration when you're deploying your cluster. If you care about network policy at all, and you should, then you need to deploy a CNI that's capable of implementing it. Otherwise, if you create network policy objects in your Kubernetes cluster, they just won't be implemented and forwarding will still be possible. On top of the Kubernetes network model's requirements, some CNIs offer additional functionality. Calico and many others offer additional functionality, and we'll talk a bit about that today as well. But let's dive in first to what network policy is. So in the Kubernetes data plane, which is the orange box, you can see that the traffic is actually forwarded. But unlike a traditional IP network, the isolation between pods is not implemented as a side effect of the structure of the network. That is to say, it's not implemented by requiring traffic to travel up through a hardware firewall. Instead, the firewall rules are implemented on the nodes as close as possible to the pods, and that has huge scalability advantages because as you add additional nodes, you're also adding additional firewall capability. Notice that the Kubernetes control plane, shown in blue, takes the network policy resources and stores the network policy resources, and the CNI's job is to take the network policy enshrined in the control plane and to actually push it down to the data plane using whatever underlying technology the CNI deems most appropriate. And different CNIs use different technologies to achieve that. Calico offers multiple choices, one of which is eBPF. So here's a Kubernetes network policy. This is what it actually looks like. We can see that the API version and the kind are highlighted in yellow. The reason for that is the API version networking.k8s.io tells us that this is a Kubernetes network policy as opposed to a custom resource type, and we'll talk more about that later. The kind is network policy, which is self-explanatory. You can see that this particular policy is called blue policy, and it applies to the namespace production. You can see that it matches any pod with a blue label, and it allows traffic from any pod with a red label on a particular port. Now notice that there's no mention of IP addresses here, and that's because IP addressing in Kubernetes is ephemeral, and we should never secure a Kubernetes cluster based on IP address because IP addresses change. So this is cool functionality, but there's some missing functionality, which anyone who's administered firewalls in their career will appreciate. And so Calico, as well as offering a fully compliant implementation of the Kubernetes network policy, Calico also offers Calico network policy. Now you can see that you have the API version here as projectcalico.org, and that tells us that this is a custom resource and that this is Calico network policy, not Kubernetes vanilla network policy. So on the left, the kind is still network policy, and we have a network policy that implements something similar, but you'll see that the syntax is slightly different. And on the right, we have a Calico global network policy. And this is an entirely new concept that Kubernetes doesn't support without an advanced CNI like Calico. Although there is talk of a new feature called admin network policy, which may in due course come into Kubernetes and create some of this functionality. Calico will obviously support that and be part of that implementation. So both of these Calico network policy types offer some advanced functionality that isn't available in a vanilla Kubernetes network policy, which is quite useful. So on the left, we see the features of a Kubernetes network policy. I'm not going to reel off that list. You can read, and there's limited time. But on the right, you've got Calico network policy, and you can see that it adds a global scope, it adds a deny action, and it adds policy ordering, as well as lots of other useful features. Now, the reason I highlight those particular features is because policy ordering and global scopes allow something very important that matters a lot to many organizations at this moment, which is shift left security policy. Now, in this diagram, what I'm trying to show is that we can see that there's some global Calico global network policy in this kind of pinky orangey peachy color, and that appears at the start and end of the policy evaluation. And that is administered by the security team of your organization. And then the blue policies in each namespace are implemented by individual teams. And what this means is we get this kind of shift left model of allowing the security team of the organization to set some guardrails. For example, maybe they want to veto a certain kind of traffic, or they want to say no unencrypted traffic, or maybe they want to pass some IP addresses. And they can do that in a way that's invisible and overrides any decision made by individual dev teams. And yet the dev teams are able to implement their own security policy, which makes them agile and able to manage their security policy as part of building their application, which is obviously very desirable for agility for development teams. All right, so I think we've said enough about the Kubernetes network model and network policy. Let's talk about eBPF, and then we'll see how those two things come together. So what is eBPF? Well, you could do an hour long or even longer talk about eBPF specifically, so I have to be a bit brief. But eBPF is a technology that allows custom code to run inside the Linux kernel. By doing so, you get the benefits that you would expect of being inside the kernel, which is you get faster performance. And it does this by implementing a virtual machine embedded within the Linux kernel. That virtual machine is heavily secured, meaning that there's an in-kernel verifier, and that in-kernel verifier's job is to ensure that the code is compliant and that it doesn't try to do anything malicious or accidentally cause problems, for example, by causing a tight loop within the kernel. An eBPF program is attached to a designated code path within the kernel, and when the code path is traversed, any additional attached eBPF programs are executed. There's lots more information at the Project Calico and Tigera websites, including a free course which actually dives into not just how Calico utilizes eBPF, but also a little bit about eBPF more generally. So if this is an interesting topic to you, then I'd encourage you to go and take a look. So here we can see just really briefly the first half of the packet flow in NetFilter in a Linux host. This image is courtesy of Jan Engelhardt. I really like this image and use it a lot, so thank you to him. So you can see that as traffic comes in on the left-hand side of the diagram, this is into a particular Kubernetes node or Linux node. You can see that it flows through this flowchart essentially, and ordinarily, IP tables and all the kind of policy that you're used to within a Linux node is implemented within mostly the green part of the diagram. But what eBPF does is you can see these attachment hooks, the ingress QDisk point and the XDP point particularly early in the flow, and eBPF programs can be attached to these points and thereby totally sidestep all the processing later in the diagram. There's also an attachment point at the end of the flow. So really, I just show this diagram to help you understand that, that by attaching early in the flow, we're sidestepping a lot of the processing that happens for each packet. So there's also something called XGP, which I won't talk about in great detail today, but this is, again, similar to the previous diagram. But you can see as the packet comes in, the network interface is capable, depending on the function of the network card, of implementing something called XDP, or it can happen in the network driver or in the Linux kernel. And XDP is a really, really early attachment point for BPF programs. And by attaching at that point, then there's a disadvantage, which is that you can't maintain flow state, but it's great for things like denial of service mitigation. And then other eBPF ingress hooks attach a little bit later, still before the NetFilter processing. So in summary, at this really high level, eBPF achieves secure, very performant networking within the Linux kernel, and it does that with small programs attached at attach points. So what are the benefits of applying eBPF to the Kubernetes data plane? Well, some of them you may be able to guess. The most obvious one is performance. The Calico eBPF data plane scales to higher throughput than the standard Linux data plane. And the flip side of that coin is it also uses less CPU per gigabit of traffic. Benchmarks are available at tigera.io, though I encourage you to test it yourself, because just how big the benefit is varies depending on the implementation details of the cluster. You also get a latency reduction, which is most noticeable with many short-lived latency-sensitive connections. So that depends somewhat on your application, whether you'll actually experience that benefit or not for your cluster. That benefit actually happens because the Calico eBPF data plane actually replaces the functionality of kubeproxy, and in re-implementing that functionality, to take a sideways step, I should say that kubeproxy is a feature in Kubernetes which implements Kubernetes services, and by re-implementing that functionality, Calico was able to achieve a much more scalable latency with many short-lived latency-sensitive connections. Now, there are actually talks that I've done which dive into this in much more detail. So if this is interesting to you, go to the Tigera website or our YouTube channel, and you should find talks there. So you also get to preserve the external source IP address. And this is a really important benefit. I'll dive into both how that works and why it's important in the coming slides. Next, you get something which is closely related, and that's direct server return. Again, that's quite beneficial, so you'll see it in diagrams in a moment. I'll talk about how that works. And finally, you get reduced complexity. As I mentioned, the functionality of kubeproxy is removed, and that means that you can actually remove kubeproxy entirely from your cluster, and it's one less moving part, one less component that you need to consider in your implementation. Now, I should say, of course, that the flip side of that is that the functionality of kubeproxy is still implemented in this data plane. So to be candid, I think the last one is the least important. I think the most important benefits here are preserving the external source IP and direct server return. So how does that source IP get preserved, and why do we care about that? So here you can see a diagram of how Kubernetes service handling happens in a normal Kubernetes vanilla cluster with kubeproxy. So this is not with the eBPF data plane. So what we're seeing here is two Kubernetes nodes in a cluster at the bottom of the diagram down here, and we have an external client at the top of the diagram. The orange box here is kubeproxy, and the purple is the flow of a client making a connection to a service within the cluster. So step one, the external client tries to connect to the cluster, and some kind of process in the network outside of the cluster makes the user or external client hit kubeproxy on the node. Now, kubeproxy immediately destination NATs and source NATs the traffic, replacing the source IP with its own IP and the destination IP with the pod IP that's actually going to serve the workload. Now, DNAT and SNAT, that's destination NAT and destination network address translation and source network address translation. Why does it need to do both of those things? Well, it needs to destination translate the traffic to make sure that the traffic then gets forwarded onto the pod on the other node that's actually going to service the user. And it needs to source NAT the traffic because it's critical that the traffic flows back through this Kubernetes node and back through kubeproxy so that it's able to maintain its contract session tables, which is a necessary part of forwarding in kubeproxy. So after it does that, the packet is forwarded onto the service pod, and the pod responds. But here's where we need to talk about what the service pod actually sees. The service pod sees a packet with the IP address, source IP address of the ingress node as the source. That means that if your workload, whatever it is, needs to log the external client IP or needs to make a decision based on the external client IP, it can't do that. There are lots of scenarios where that's really important. For example, perhaps you have a compliance requirement where you need to log the external client IPs of your users. The only way to achieve that here with this data plane would be to use some kind of other logging outside of the service pod, which means that the end engineers who need to administer the service won't easily be able to relate connections to particular external clients. Another example might be that you only want to restrict your users based on GeoIP, so maybe you have some copyright requirement, or maybe you want to offer something like a VPN service to users in a certain jurisdiction. The response goes back and the source and destination IP addresses are reversed, and that happens back on the ingress Kubernetes node. Finally, the external client gets the reply. So notice that both nodes are involved in the traffic flow, both on the ingress and the egress, and that the service pod never gets to see the IP address of the external client. So let's contrast that with how this actually looks with a Calico eBPF data plane. So again, you have the Kubernetes node on the bottom left and the Kubernetes node on the bottom right. Nothing's changed there. But you'll notice that the kube proxy is entirely missing from this diagram. So the flow is shown in purple as before. You can see that the external client makes a connection, and as before, the external network makes sure that that traffic reaches the outside of one of the nodes. For argument's sake, the service pod in both this diagram and the previous diagram showed the service pod on a different node to the node that was selected by the external network. But of course, it's possible that the service pod could be on the same node. So the first step in with the eBPF data plane is that the BPF program spots that the packet is destined to a service. It makes a load balancing decision and sends the packet to the node hosting the pod. Notice that there's no mention of network address translation here, and that's because no network address translation occurs on the ingress node. The next step is step 2. The BPF program on the node that actually contains the service pod does a destination NAT. And it has to do that because otherwise the service pod wouldn't accept that traffic. So there's no way or no reason to want to avoid doing that. But notice that there's no source NAT here. There's no need for a source NAT to occur. The traffic is forwarded onto the service pod, and the pod is able to log the real source IP of the external client. So to labor the point, if that happened to be a web server, then the web server logs would contain the real external client source IP, and that means that the guy or person who's administering the web server would be able to see the real source IP address and could troubleshoot or log or secure or mandate decisions based on that IP address. The next thing that happens is that the pod responds, and the BPF program on the node containing the service pod actually reverses the destination NAT. Now, the next thing is that if the upstream network allows it, the packet is able to return directly up to the external client. Unfortunately, not all upstream networks do allow that, and there's something called unicast reverse path forwarding. It's a security feature of IP networks that sometimes means that it's not possible to return the traffic directly. And in that scenario, it's entirely possible to ensure that the traffic with the Calico eBPF data plane still goes back through the ingress node if necessary. But if the upstream network does support it, then implementing this feature means that the ingress node never needs to be involved in the flow, and that you still have logging of everything, but the latency is slightly reduced, and the network load on your Kubernetes nodes is reduced, which brings another performance benefit. So these are the key benefits of implementing the Calico data plane using eBPF. So just briefly, why might you not want to do this, and why? And if you do want to do it, what are your next steps? Well, there are much longer talks that I've done which specifically talk about these considerations, so you can go and look for those if you'd like to. I'm low on time already, but briefly speaking, there are certain requirements and restrictions around the Calico eBPF data plane. The primary one is that the nodes, the Kubernetes nodes, need to have a certain kernel version to be able to support eBPF. In addition, the cluster needs to support, not utilize other features such as IPv6, and all of these restrictions and requirements can be found on the Tigera or Project Calico websites for eBPF. So if you go to the Getting Started, probably best to search, use your favorite search to search for eBPF data plane Calico. You'll find the Getting Started, and on that page you'll find all of the specific restrictions and how to get started depending on the kind of cluster that you are running. So that's all I have time for. I hope you found that talk useful, and if you did, or if you want to chat with me, you can reach me through all the usual social channels, as well as through SUSECON. And if not, then go to our documentation, and you can follow up there and learn a great deal more. Thank you so much for attending.